The first time I taught this course, as I go through chapter 4, I got the impression that it was like overkill. I kept saying to myself, oh, I've taught this, students should know this. But you need the reinforcement. So a lot of these ideas that we're going to be looking at in section 4.2, hopefully they make sense to you, and if they don't, then it'll just be a matter of continuing to think about it and try to connect this with section 4.1. But many of you will see that this is the same as 4.1. We're going to be looking at finding coordinates of what are called extreme values. And we're going to be looking at a couple of different types of extreme values. Some are called absolute and some are called relative. We're also going to be looking at functions' behavior over a closed interval as opposed to functions' behavior over an open interval. What does that mean? Well, if I have a function and I tell you it's defined everywhere from negative infinity to infinity, then that's considered an open interval. X is an element of real numbers, or X is an element of negative infinity to infinity. If I tell you, however, and it doesn't matter why this is the case, but I tell you a function is defined only over a closed interval, I'm telling you it's defined from some value of x to some other value of x. So maybe I'm saying it's only defined from x equals 1 to x equals 10. And by the way, you could write that domain as x is an element of, with square brackets, a to b. So a closed interval is an interval that starts in a specific location and ends in a specific location, whereas an open interval in the context of what we're talking about means any real number. So we have some definitions to begin with here. The first definition is of what we call an absolute maximum. And the word absolute here has nothing to do with absolute value or anything like that. It just means it is the absolute maximum. There is no place else on this function that is bigger. And we're talking here about it being the highest value of the function, and it will serve you well to remember that the function is y. So an absolute value of a function is the highest value that y ever has on the graph of the function. This is sometimes called a global maximum. And I don't think your textbook uses that. If they do, it's just in passing and it's not important. But I've seen some post-secondary instructors use global. And global just means everywhere. On the other hand, an absolute minimum of a function is the lowest value of the function, the lowest value of y, over the entire interval that the function is defined. Now, that's sometimes called a global minimum. A function doesn't have to have an absolute maximum, because if you look at the graph of a function and the function goes up forever, like y equals x squared goes up forever, there is no global maximum. There is no absolute maximum because the thing just keeps getting bigger and bigger. And a function doesn't necessarily have to have an absolute or a global minimum. If the function continues to decrease towards negative infinity, then there's no minimum value of the function. So you can have some functions that have both a global maximum and a global minimum, or absolute maximum and absolute minimum. You can have some functions that have only one or the other, and you can have some functions that have neither. There's another type of extreme value. We call these extrema, which is plural for extreme value. And that's called a local extrema. And a local maximum is a point that the function exists with the high value or a highest value possible in that region. There might very well be other places on the graph where y is bigger, but in that region, y is big compared to the surrounding graph. I'll show you what that means in a bit. And that is sometimes called a relative maximum. So you have all these words swimming around. Again, it's not that you need to memorize these or anything, but if you see it, think of the word relative as just meaning in relation to the graph in that vicinity. And the word local simply means in that area. And we can also have, finally, a local minimum. A local minimum exists wherever the function has a minimum value in a particular area, which means that the surrounding graph is higher than that point because that point is as low as possible in that region. And this is sometimes called a relative minimum. So in order for you to appreciate what this means, we're just going to go through an exercise here where you're asked to label all maxima, which is a way of pluralizing maximum, and minima of that function. And I think the most efficient, reasonable way for us to do this so it makes sense to you is to first of all label all of the points that are going to be extrema. So take a minute and label all of those points. And now we're going to talk about local minima. So which of these points is considered a minimum value of the function? Well, point A is. A is a local minimum. Why is A a local minimum? Because it's basically at the bottom of a curve. When you take a look at the region to the left of A and the region immediately to the right of A, the graph is higher than it is at A. So point A is called a minimum value of the function. It's not the absolute minimum. There's no way it's the absolute minimum because if I take a look at point C or point G or lots of other points are even lower than A. What's another local minimum? Well, C is definitely. When you look at the vertical position of C, in that region where C is lower than the surrounding portion of the graph. E is also a local minimum because when you look at the region surrounding or next to E, E is lower than that region. And G is also a local minimum because when you look at the graph close to G, G is lower than all of the rest of the graph close to G. I'm going to pause there. Does anybody have any questions about identifying those 4 points as being local minima? Okay, I'm going to jump down to absolute minimum and I'm going to label G. Because G, as well as being a local minimum, which means it's the lowest point in that vicinity, G is the lowest point on the graph, period. If I were to put my eyeball along this line and look at G, this is my eyeball, I can see the graph there. But if I were to go anywhere lower, I will never, ever encounter that graph, which means G is as low as it goes, and that means it's the absolute minimum. I'm going to go up one notch here and look at the absolute maximum and just make a note that there is no absolute maximum. And the reason is because the graph increases indefinitely. What does indefinitely mean in this context? It means it keeps going higher and higher and higher and higher. So there's going to be some point on the graph where y is 10 gajillion. And you might say, well, is that the maximum value of y? Is that the maximum value of the function? Well, no. Because if you go a little bit further, it's going to be 10 gajillion and 1. And it's going to just continue to increase and increasing. The maxima would be point B, D, and F. Because in those regions where those points are located, B is at the top of something, D is at the top of something, and F is at the top of something. Does anybody have any questions with identifying those points? All right, I do want to point something out to you here. Get my points back. That if you look at all of those red points, and we're going to talk in detail about this in a second, but it's crucial to what we're learning today. At all of those red points, the derivative is either equal to 0 or the derivative is undefined. And I'm going to come back to this graph a little bit later and explain to you why each and every one of those points has a derivative that's equal to 0 or a derivative that's undefined. In other words, piggybacking off of Friday's lesson, these are all critical values for the derivative. So keep that in mind. All right, warm up. A function is defined by negative x squared plus 8x minus 22, but it's defined only from 1 to 5, including 1 and 5. So this is what we refer to as a closed interval. And how you answer this question is really, really different than how you answer a question if the interval is open. What's going to happen is, at the end of all of this, you will see a problem like this, say, on an exam, and you will do it wrong maybe because you're doing it as if it's an open interval. And the key difference I will tell you right now is this. You do not use a first derivative chart to answer this question. Whereas if it's an open interval, you have to use a first derivative chart. A first derivative chart is what we were doing on Friday. Okay, well, in order for you to determine the maxima and minima, graphically, we're just going to look at the graph of the function. So you're going to take your graphing calculator, and I've thought long and hard about this, and I think doing this on a graphing calculator is the best way to learn about what a closed interval is. So you're going to graph this function. We can enter in the function, which is negative x squared plus 8x minus 22. Now, we won't worry about looking at the graph right now. We know this is going to be a parabola. But because of that restriction on the domain, this graph is not a parabola. It's only part of a parabola. We only want to look from 1 to 5. So in my window setting, I'm going to go from x equals 1 to x equals 5. Now, what do I put for my window settings vertically? Well, I'm going to go to my table, and I'm going to explore using my table what the y values are in that domain. The y values for min and max that I have in here are just from some other thing that I was working on. It doesn't matter. So I'm going to set up my table to start at 1, and I'm going to go up by 0.5. And when I look at my table, I can see that when x is 1, which is at the beginning of this graph, y is negative 15, and y increases and increases and increases, and then when it gets to 5, y is negative 7. So this graph climbs, and actually, you know what? It climbs past negative 7, and then it starts dipping back down to negative 7. So it looks like negative 6 is as high as it goes vertically, and I think it was negative 15 is as low as it goes. So for my window setting, let's go negative 20 to 0. That'll cover it. So when I graph it, I'm looking at this graph. Remember, if you're trying to find the absolute maximum and absolute minimum, that means the point that is bigger than every other point. And we do have a point that is bigger than every other point, vertically anyway. And that point is at the top of this hill. It's right here. And we do have a point that's as low as it gets. There's no other point that's lower than that other point I've indicated. So this is corresponding to the absolute minimum, and this is corresponding to the absolute maximum. So what were we asked to find? What are the coordinates? So we need to know the coordinates of these 2 points. Well, this occurs at x equals 1. We don't know the x coordinate that this occurs at. We'll find that out in a second. But in order to find the y coordinate of this first point, I can just look in my table, and I'll remind you that it was -15. So this point, the absolute minimum, is at 1, -15. This is not an interval. These are the coordinates of a point. Now, how do we find graphically the coordinates of this point? We can go to our Calculate menu, second trace, choose maximum, because it is on the top of a curve, put our cursor to the left of that point, put our cursor to the right of that point, hit enter a couple more times, and we get the coordinates as being 4, 6. So the absolute maximum is at 4, 6. And we've answered the question. Does anybody have any questions with that first example? Okay, now we're going to get into some stuff that's tough to think about. It's not just algebra or math. I want to explain to you the significance of what it is we're doing here. The extreme values, there's a couple things I want to talk about, but the first one is that those extreme values, whether it's in the warm-up or the first example, are always where the derivative is equal to 0 or where the derivative is undefined. And I'm going to go back to our warm-up, well, this part of the warm-up, and I want to indicate to you the points where the derivative is equal to 0. The derivative is equal to 0 on this function at a, c, d, e, and f. And the reason the derivative is equal to 0 at those 5 points is that the slope of the tangent at all of those points is 0. I hope that makes sense. Some of you might say, well, isn't the slope of the tangent at b 0 as well? And the answer is no. This is going to require a little more explanation, but let me finish my statement here about the derivative and its meaning in terms of being equal to 0 or not defined. The derivative is not defined in the above function at b and g. So I have a couple of questions I want to throw your way and ask you to think about for a minute. One of the questions, and you don't have to answer this one, you can answer the next one if you like, is why is the slope of the tangent at b not 0? That's one question that I think is important to ponder. And better yet, why is the derivative not defined at b or at g? What is it about those 2 points that says the derivative can't exist? And this is a difficult question. The comment is being made about it not being continuous. And although we could make an argument that it's not continuous at G because it's missing another side, the graph is continuous at B. Now, when we first talked about continuity, I told you there was an exception to everything we were saying about continuity, and this is basically the exception. B is continuous, but the derivative doesn't exist there. So there's a better way to explain it. We're getting there. Let's go back to the original definition of the slope of a tangent, which morphed into the definition for a derivative. If we wanted to know the slope of the tangent at this point, then what we did was we took another point and we said, let's draw and calculate the slope of the secant. And then let's move that other point. This was P and this was Q. Let's move that other point, Q, someplace else and calculate and draw the new slope of the secant. And I hope you all remember that. And what we said was that the slope of the tangent, this was what we said, and I hope you still remember this, is the limit as point P approaches Q of the slope of the secant. I hope that is memorable to you. But then we learned about left and right-handed limits. And if we were in front of each other, I would ask you and look at your nods or shakes in response to this question, but I'll ask it anyway. How many of you remember that I said there's only one reason why we're studying left and right-handed limits, and it's so I can refer to it later in a particular lesson? This is the lesson. We said that in order for a limit to exist, the left-hand limit and the right-hand limit have to be equal to each other. Okay, so if I have some function and it looks like this, and this is point P, the slope of the secant on one side looks like this, the slope of the secant on the other side looks like that, and although you could probably argue that each of those two slopes are going to approach some number, they won't approach the same number, because the slope of the secant on the left is negative and the slope of the secant on the right is positive. So if this is what we're talking about, where this is point Q, which can be in any position on the whole function, this doesn't exist. This is not defined. And that means the slope of the tangent doesn't exist. So going back to my graph, at point B, and I'm just going to get rid of this thing, at point B, the slope of the tangent doesn't exist. There is no defined value for the slope of the tangent. And since the derivative is defined as the limit of the function as h approaches 0 of f of x plus h minus f of x all over h, the same would be true of the derivative, because the left-hand limit and the right-hand limit are not equal to each other. It gets even more obvious when you take a look at point G, because at point G there isn't anything on the right-hand side. So you can't even have a left and a right-hand limit. You only have a left limit. If we were to take a look at our example that we did with this warm-up, the derivative here on the left and the derivative here on the right are not defined. So the derivative of a function is not defined wherever the function starts or ends or has one of those kind of weird corner pieces. The derivative here, I hope you see, is 0. So getting back to our notes now, this is the point that I'm making. You might run across this in your textbook, and in post-secondary next year we have a special name for this It's called Fermat's theorem. There's something else I want to talk about, though, before we get to a couple of examples. I've already talked about this. That corner point, point B on our graph at the top of this lesson, is sometimes referred to as a cusp. So keep your eyes peeled for that. I'm struggling a little bit here today because I'm trying to explain all this, but I can't see your faces. So I'm going to pause. Does anybody have any questions so far about the explanations as to what is going on? Or comments? All right, one other point I want to make. No, we'll make it later. So, no, I better make it now. These points where the derivative is 0 or not defined are called critical values of the derivative. Now, listen very carefully. This is tricky. Whenever you have a maximum or a minimum on a function, it has to occur at a critical value. Okay? So if there's a maximum point, at that point, the derivative is either equal to 0 or it's not defined. Okay? But just because a point has no defined derivative or a derivative equal to 0 doesn't mean it is a maximum or a minimum. That's very, very tricky. What I'm telling you is all max and min have to be critical values of the first derivative, but not all critical values of the derivative are max and min. And there's a very simple analogy I can give you here, that all chickens are birds, but not all birds are chickens. And that's what we're saying here is all max min rather, must be critical, but not all critical are max min. So in the collection of all critical values of a first derivative, some of those are going to be max mins, some will not. And that's why I've got here, think of the critical points of the derivative as being points that we think might be max mins. All right, let's take a look at example 1. Describe 3 different situations where critical values can exist, yet not correspond to a maximum or a minimum. So I want you to think about this. I want you to see if you can come up with a graph in your mind where at some point the derivative is equal to 0. Okay? The slope of the tangent is 0, but it's not a maximum or minimum. And I know I'm really pushing it today and really asking you and challenging you to think about these things, but I think it's important. How can a graph have a slope of 0 at a point, but not be a maximum or a minimum? And there are a couple of ways that can happen. And that's one of them. A horizontal line, yes. I'm not going to include it in our 3 here, but I'm going to include actually a 4th one, because I think this one is kind of, we could argue about this one. Let's say that we have a horizontal line. So f of x equals 6. So we have the function y equals 6. I'm not going to include that because technically, mathematically, a mathematics prof would say there is a maximum value. The maximum value of this function is 6. I disagree with this line of thinking, but this is what they would say. They would say the maximum value is 6, and I would go, well, what are you talking about? They would say, well, is there any value that's lower than 6? No. Is there any value that's higher than 6? No. So 6 must be both the maximum value and the minimum value. And that's one of the ways we can say the derivative is equal to 0, but there's no maximum. I'm thinking now, though, about a situation where it's not horizontal, though. No doubt here, this is a legitimate answer, but it's not the one I want everybody to focus on. How can we have a curvy graph where there's some point where the slope is 0? Oh, okay. So it's asymptotic. That's one of the ways. Except if we have an asymptote, the function isn't defined at that value of x, which means the derivative will not be defined. And I'm going to put that, but this is not a case where the derivative is equal to 0. So this is one of the answers to the question, where we have an asymptote. And maybe the graph looks like this and like that. And there will be a critical value here at this value of x. I'm going to call it a. But at a, the derivative is not defined. So that's one of the three situations. There's a critical point at A. Why is the point at A critical? Because the derivative is not defined, and yet there's no maximum or minimum. Is there a way we can get an actual slope equal to 0, though, and have not a maximum or minimum? In other words,
Could it?
Go ahead, Aaron.
Could it be if it's like coming? I'm not sure what. I think we had one last year. I'm not sure what the graph, the function was actually, but what if it's coming in from the bottom and then kind of flats, it evens out into like a horizontal line and then goes back up? Does that work?
Absolutely. And that would be an example of an inflection point. Now, not all inflection points look like that. Like an inflection point could look like this. That's an inflection point in here. But here, the slope is 0 at this point. It flattens out to 0. That's exactly right. So the slope of the tangent, I'll draw it in with a different color here. The slope of the tangent here is equal to 0, which means the derivative, well, I'll stick with the f prime notation, which means f prime of a is equal to 0, but that is not a maximum or minimum. So if you go back and look at the work we did prior to this example, every single max-min was a critical point. But what we're saying is just because you have a critical point doesn't mean it's a max-min. Any ideas for a third one? Oh, perfect. What about like a parabola that's rotated 90 degrees? And are you talking here about the vertex of that parabola? Perfect. So I never thought of it that way. I have a different way of explaining this one. You're talking about something like that where, I'll move it over so I can label A. You're talking about this, where the point of curiosity is here, and f prime of a is not defined. Shiv, can you explain why the derivative is not defined there? And I'll give you another way to explain it. Can you tell me what the slope of the tangent is there? Can anybody tell me what the slope of the tangent is at that point? Right here. It's infinite. Yeah, it's infinity. And infinity is another way of saying not defined. By the way, it doesn't have to look like that. I'm going to draw on here, and I hope you're finding this worthwhile. We don't have to explain all this, but I think it's worthwhile. I could take the graph that Aaron suggested, which is the middle one, and twist it a little bit so it looks like this. And I could say that there's another point here, I'll call it B. F prime of B would not be defined. So it could be an inflection point, or basically, as Shiv pointed out, any point where the slope of the tangent is going to be a vertical line. And just for kicks, I'm going to show you one last one. This one is, I don't claim to be the person that came up with this. A student came up with it one time. They said, well, what if you have a parabola? And I think this is wild to think about, that looks like this, except there's a hole at what would be the top. So the derivative is not defined there. It's definitely a critical point. The reason why the derivative is not defined there is the function doesn't even exist there. And if a function doesn't exist, the derivative doesn't exist. And I disagreed with the student initially and said, well, yeah, but there's a maximum value. I said, well, what if this point here is at 7? And they said, well, the maximum value of the function isn't 7. And I started thinking about it, and I thought, well, they're exactly right, because there's a hole at 7, so the function never reaches 7. And the student explained it very well. She said, if you think that the maximum value of the function is 6.99999, you're wrong, because there's a point where it's larger than 6.999. There's always going to be a point that's larger. It's going to be getting bigger and bigger and bigger and bigger, but it will never reach some maximum value, which is kind of interesting. All right, let's move on. I think we've talked that kind of to death. The bottom line here is that critical points may or may not be max mins. All max mins must be critical points. So we want to find the absolute maximum and minimum of this function. It's a closed interval. So what we need to do is make a list of the suspects. We need to make a list of the places where the derivative is not defined or equal to 0. These are the critical values of x. So let's find the derivative. dy dx is found by wrapping that 2/3 around the base, which stays the same, dropping 1 from the exponent, and then multiplying by the derivative of what's inside. I'm going to simplify that so that we can talk about the critical values of x. I'm going to write this as 4x on the top, and then x squared minus 9 to the 3rd on the bottom. Any questions with, and there's a 3 on the bottom as well. Any questions with getting the derivative? Okay, I hope you would agree that a critical value of x would be 0, because 0 on the top makes 4 times 0, 0, which makes the whole derivative 0. Another critical value of x is negative 3. Another critical value of x is positive 3, because the bottom can be factored into x plus 3x minus 3. Still good, I hope, but I'm going to tell you right now that there are 2 other critical values of x. And I want you to think about what they are and let me know if you can come up with them. Remember, critical values of x happen where the derivative is 0. So that would be at x equals 0. And where the derivative is not defined, which would be where x is 3 or negative 3. But I'll tell you there are 2 other points where the derivative is not defined. It would be, Dan, because that's where the function starts and where it ends, so the derivative is not defined there. Now, I need to talk about something which for some reason I skipped over, and it's in your notes. But if I have an interval that goes from one value of x to another value of x, and the function is continuous from that value of x to some other value of x, it doesn't matter what it does, there has to be an absolute maximum and there has to be an absolute minimum in there. So one of these is going to correspond to an absolute maximum and one is going to correspond to an absolute minimum. We just need to find the y coordinates for each of those points. And whichever y coordinate is the largest, well, that will be the maximum value of the function. Whichever is the smallest will be the minimum. So I'm going to use my graphing calculator here. I'm going to enter into y, the function. And this is essentially what we did with the first part of this lesson. We simply looked at the y coordinates of all of the critical values of x. So I have in brackets x squared minus 9 n brackets raised to the 2/3. I'm not going to look at a graph, though. I'm simply going to set up my table to be on automatic. Sorry, to be on ask. Go to my table, and I'm going to enter 0 for x. Okay, the y coordinate is 4.3 something. What about -3? Or 3, or what was the other one? -10, which is where the function starts, or 4. Which of those is biggest? Well, the one where x is -10 is the biggest y value. So the maximum value of the function is f of -10. You know what, quite frankly, I don't even care what it's equal to. You would put 10 in there and solve this equation and get, I guess, 91 to the 2/3. But I don't care about that. You could calculate that number. Which is the smallest? Well, f of -3 and f of +3 are both as small as possible. So the absolute minimum is f of -3 or f of 3, which is 0. The min is f of -3 or f of +3, which is 0. Any questions with that example? Again, everybody, if it's a closed interval, which is what this is, you don't do a first derivative table. You simply line up all the suspects and you find out which one is as tall, which one is the tallest and which one is the shortest, basically, in terms of y. Let's take a look at the last example, example 3. Find the critical numbers for that. So what are critical numbers? Critical numbers are where the derivative equals 0 or where the derivative is undefined. So we find the derivative. Nope, that was right. So I swing the exponent around and drop one from the exponent in both of those terms. I want to factor now the lowest exponent out, which would be x to the -3rd. That's going to give me 3x raised to an exponent and then plus 2. I want everybody to figure out what that exponent is going to be. It is the exponent to which you add to -1/3 to get to 2. And I'll give you a hint, 2 is 6/3. Will be 7/3. That means my derivative can be expressed as 3x to the 7/3 plus 2 over x to the third. What are my critical values of x for the derivative? Well, 0, because if I put 0 into the denominator, I get 0 in the denominator, which means the denominator being 0 makes the whole thing undefined. You cannot divide by 0. I also get, there's a little bit of thinking here that has to go on with the top. I need to take 3x to the 7/3 plus 2 and set it equal to 0. So I'm going to subtract 2. I'm going to divide by 3. And then I'm going to raise both sides to the reciprocal of the exponent. Because x to the 7/3 raised to the 3/7 is a power of a power, and I multiply those exponents and get x to the 1, which means negative 2/3 to the 3/7 is the other critical value of x, which is a weird number. So if you take negative 2/3 and take the 7th root of it, let me clean that up a bit, take the 7th root of it and then cube the result, you will get that number. I would like everybody to just throw that into your calculator right now. I want you to take, you're going to have to use brackets, negative 2/3 raised to, in brackets, 3/7, so that we have some kind of number that we can look at. So I'm getting about negative 0.84. Anybody else get that number? Yeah. Okay. All right, so how are we going to define? We've decided on what the critical values of x are, 0 and this crazy number. How are we going to decide if they are max-mins or not? They could be, but they might not be. What we're going to do is a chart. We're going to go from negative infinity to 0, from 0 to that wild number, and then from that wild number to infinity. And admittedly, everybody, I'm adding this part to this example to lead in to tomorrow's content. Across the top, we're going to put 4x and 3x to the 7/3 plus 2. I want to go back and just make sure I wrote that down correctly. I did. Oh, it's not 4x, it's x to the third. I must be thinking of a different example. So these are the factors of the derivative, because it's 3x to the 7/3 plus 2 over x to the third. You don't quite, well, you might realize why I'm doing this chart, but again, I'm using it to teach you, to lead into tomorrow where I explain why this works. The 0 of x to the third is 0, so before 0 it's negative, after it's positive. Over here, this is going to switch when we pass the 0 of it. This factor at the top of the page here, 3x to the 7/3 plus 2, is not linear, but it follows the linear rule because the exponent is odd. There's no squareds. So the derivative is positive, then it's negative, then it's positive. So what is the function doing? Increasing, decreasing, increasing. That means there's a maximum value here. Think about this for a second. We're going to do this in the next lesson. I keep saying tomorrow, but it's the next lesson. If the function is going up and then the function is going down, it has to go through a maximum. And if the function is going down and then going up, it has to pass through a minimum. So the critical value of x of 0 corresponds to a maximum value on the function, and the critical value of x being that crazy number corresponds to a minimum. I know this has been a long lesson fraught with a lot of deep thought, but let me show this to you graphically. So y is equal to x cubed plus 3 times x raised to, in brackets, 2 divided by 3. I'm going to go zoom 6, which is the standard. That's what the graph looks like. I'm going to go zoom box and just zero in on it a bit more. It's kind of a crazy looking graph. I must have something in my stat plot. There's a point there. So there's a peak right there. There's a maximum value of the function, and then there's a minimum at the origin. While the x-coordinate of that maximum value of the function is that crazy number. I've got something backwards here. Just give me a second.
I have a question.
Yeah.
For the intervals, isn't the weird number less than
Oh,
0?
shoot. That's what I got backwards. So these, I wrote my columns in the wrong order, right? This number, thank you, Aaron. This is the wacky number. What a horrible mistake to make. Was it to the 3/7?
Yes.
Okay, so this is negative 2/3 to the 3/7. This is 0. So there's a maximum at that number. I didn't put them in the right order, which is a fatal mistake. Thank you for catching that. Anyway, in the next lesson, we're going to get a lot more practice with these charts. And I feel bad about putting that in the wrong place. This is the first time I did this where I didn't draw a line and talk about slicing it. And that's what I should have done, because that negative 0.84 is here and the 0 is there. So I should have gone from negative infinity to negative 0.84. It's actually a good thing we checked with the graph. Anyway, you've got a few questions. We'll work on this for maybe, I don't know, 20 minutes. The next lesson is not a long lesson. It only has a couple of those. Aiden is asking, would those be local because there is no limit on the function? I want to just add something to that first, Aiden. Even if they were maximum, even if they were absolute rather, they would still be local. But these are not maximum, which is I think what you're getting at, because the function goes up and down forever. So when you actually take a look at the graph continues up forever and continues down forever. So this is a local max, This is a local min, but they are not absolute. Am I answering your question? Okay, good. So remember when you're working through these, everybody, that if it's a closed interval, you do not do the chart. You simply find the critical values of x and determine the y coordinate for each of those points. If it's an open interval, you have to do the chart. And don't make my mistake. Make sure you put your intervals in the proper order. Otherwise, you'll get all of the answers backwards. So I'll give you guys about 20 minutes or so to work on these. And if you have questions, just give me a shout or type something in chat.